Hello, students of Standard 11. I'm Dr. Susan George, and I will be teaching you Chapter 7 in Physics Systems of Particles and Rotational Motion. So, let us start with an introduction. First, let us define a particle. What is a particle? A particle is represented as a point mass. It practically has no mass. A point mass, there is a mass, but it cannot be measured. It is so tiny, so small that it cannot practically be measured. This is what we call as a particle. So a particle is a point mass. Next, what is a real body? A real body is something which has a finite size and mass. That means it has a measurable size and mass. Next, what is an extended body? An extended body is a system of particles. It can be a two-particle system or a three-particle system, but we consider it together as a rigid body. Now, what is a rigid body? A rigid body has a perfectly definite and unchanging shape. When you apply some deforming force to the body, it does not change its shape. And the distance between all pairs of particles do not change. That means all the particles will be remaining in its same position in a rigid body. Next, we will see what are the different types of motion of a rigid body. The first type of motion is pure translational motion. And we can see an example here of pure translational motion. There is an inclined plane AB and a block which is sliding down that inclined plane. P1 and P2 are any two particles of the block. Now, as the block slides down, P1 and P2 will have the same velocities. Their position will be same. So it means that all the particles will have the same velocity in pure translational motion. Another example, you can see a pot which is moving in translational motion. So O is the center of mass of the pot and P is any particle in the first instant of time. And you can see a vertical line drawn from O to P. There is a horizontal line also drawn here from O. So in the first instant of time, we'll call the particle as P1 and the center of mass as O1. You can see these two arrow marks are pointed in the same direction according to the tangent of this curve. That means every particle of the pot will be moving in the same direction. Let us take the second instant. Here, the pot has come to this position here, and the curve of translational motion is almost straight. So P2, the arrow mark from P2 and the arrow mark from O2 are again parallel. That means all the particles of the pot are moving with the same velocity. Here once again we have the third instant of time and we have P3 and O3 also, all the particles which are moving with the same velocity in the same direction. Next we can see what is the angle between this vertical line OP and the horizontal. Here it is represented by alpha 1, here it is represented by alpha 2, and in the third instant it is represented by alpha 3. So when you observe, you can make out that alpha 1, alpha 2 and alpha 3 are equal. So in conclusion, the velocities of particles at O and P are same at any instant of time. The second conclusion, the vertical line OP makes an angle alpha with the horizontal such that alpha 1 equal to alpha 2 equal to alpha 3. So these are the features of a pure translational motion. The second type of motion of a rigid body is pure rotational motion. And in pure rotational motion, we have two types. The first one is about a fixed axis. So one example is a ceiling fan. You can see the axis of rotation represented by dotted lines, and this is fixed, and the leaves of the fan rotate about that axis. The second example is a potter's wheel. You can again see the dotted lines representing the axis of rotation, and you can see the potter's wheel keeps rotating about that axis of rotation. This is pure rotational motion around a fixed axis. This is a rigid body. The fixed axis of rotation is OZ, and we are considering two particles P1, P2, and one more P3. So P1 and P2 you can see are at different distances from the axis of rotation, and P3 is on the axis of rotation. What happens when this rigid body rotates? When the rigid body rotates, P1 makes a circle in a plane perpendicular to the plane of the rigid body with C1 as center. What about P2? When the rigid body rotates, P2 also makes a circle in a perpendicular plane with C2 as center. And what about P3? P3 is on the axis of rotation, so it cannot make any circle, and therefore it remains stationary. So every particle moves with different velocities in pure rotational motion. A rigid body rotation about the z-axis is shown here, and we know the radius of the circle is the perpendicular distance of the point from the axis. But P3 remains stationary. In pure rotation of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Now, the second category of rotational motion is when the axis is not fixed. So, one example is the spinning top. As you know, a spinning top, once it is set into motion, it keeps rotating at the same time. It rotates about this axis of rotation. This is the axis of rotation. At the same time, this axis of rotation also keeps moving in a circle. All right. So there is movement. But what happens here? This point, the tip of the top and the ground will be fixed in a fixed point. So there will be rotation, but the axis will not be fixed. Now this circular motion it exhibits is called precession. Another example for the axis not fixed is a table fan or a pedestal fan which is oscillating. So here we have the fan. The leaves of the fan keeps rotating. This is rotation about an axis. But this axis is not fixed because this table fan will oscillate from left to right, then from right to left, and then again from left to right. So since it's oscillating, this axis is not fixed. But what is fixed? This point O is fixed. So when there is rotational motion where the axis is not fixed, there will be a point which is fixed. The third type of motion of a rigid body is a combination of translational and rotational motion. You can see an example here, an inclined plane and a cylinder rolling slowly round the plane. So we can have some particles P1, P2, P3 and P4 represented on the cylinder. And you can see that the particles are pointing in different directions here. So their velocities are not same. So there is rotation here as well as there is translational motion. So this cylinder keeps rotating as it rolls, and at the same time it moves in a straight line also. So this is a combination of translational and rotational motion. So here at the point of contact P3, the velocity is 0. This is another example of combination of translational and rotational motion. Here, the pot is rotating, as you can see the three different positions. So, O is the center of mass, P is any particle. Here, both arrow marks are in the same direction. The vertical line from O to P and the horizontal line here makes an angle alpha 1. Look at the second instant of time. The vertical line has changed its position and therefore alpha 2 will be different or smaller. And P2 is pointing in this direction whereas O2 is pointing in another direction. So here the particles' velocities are different. Look at the third position. The pot has come to another rotating position. So OP and horizontal line will be alpha 3. It will be different. And we have P3 pointing in this direction and we have O3 pointing in this direction. Therefore, the angle will be different. So we can conclude. In the case of combination of translation and rotation, the velocities of O and P differ. Also, alpha 1, alpha 2 and alpha 3 may all be different. Then, the motion of a rigid body which is not pivoted or fixed in some way is either a pure translational or a combination of translation and rotation. Also, the motion of a rigid body which is pivoted or fixed in some way is rotation. So, we will stop for the time being. Thank you, students.